Hello everyone, today we are going to discuss the topic of electric field. An electric field can be considered as an electrical property associated with each point in the space where a charge is present. Okay. An electric field is also described as electric force per unit charge. Okay. Now let's say this charge is present and in the environment near it, you will feel the electric field. Okay, this is an electric property. Now, if you look into the units, force is given in newtons and charge is given in coulombs. So Newton per coulomb is the SI unit for electric field. Okay. Now, moving ahead, the direction of the field is taken as the direction of the force, because as you see, electric field is a vector quantity, right? So that means it will have its magnitude, okay, and then plus direction, okay. This is what your vector quantity means, right? Electric field is a vector quantity. That means it should have magnitude as well as direction. Now, magnitude we can have by plugging in the numbers and finding the answer, but what about the direction? So for the direction, the direction of electric field is taken as the direction of the force, because if you see over here, F upon Q. So F is also a vector quantity, Q is a scalar quantity. That means, so the direction will be considered as direction of force. Okay, so the electric field is radially outwards from the positive charge. Now let me just quickly draw something here for you. Let's say I have a positive charge over here. So how does electric field looks like? So these are called electric field lines. So the direction of field is taken as positive. Uh, it is radially outwards for a positive charge. Okay, so these are field lines that are coming from a isolated positive charge. Now if I have to draw for a negative charge, let's say I have a negative charge, so how would the electric field lines look like? It will be coming in. Okay, so you can draw a nice diagram like this. So they will be coming in, so they are radially towards the negative point charge. Now moving on, if we have, let me move on to the next slide over here. So electric charges experience forces from the other charges, right? So let's suppose we have this charge over here, Q naught. Sometimes it is also referred to as the test charge. You can call it a test charge or a charge which why it is called a test charge, because it is useful to think of it as a test charge because it can help you determine the extent of the charge or the force that is being experienced by this charge over here or at this point due to the other surrounding forces. Okay, so electric charges experience forces from other charges. Okay, so let's say if we have two positive charges, right, and they will repel each other, right? So we say that electric charge setups an electric field around them, right? So this electric field then affects the other charge which are near them, which are present in the vicinity of that charge. Now, uh, let's see this thing, a question. Let's try to solve the question over here, which says that the positive just charge that is shown over here, the value of the charge is Q naught is given as 3 into 10 to the power minus 8 coulombs, and it experiences a force of 6 into 10 to the power minus Newton in the direction shown in the drawing. Okay, so it feels the direction and force in this direction. First question is find the force per coulomb. Okay, so you have to find how much force is being exerted on this charge over here if you have 1 coulomb. Okay, but for each coulomb, how much force is being experienced by this test charge. Okay, so in other words, we are just finding electric field because I just told you E is nothing but F upon Q naught, right? Okay, so let's dive into this one. Let me write the values. F is given over here. I'll write this thing 6 into 10 to the power minus 8 Newton, and then I have Q naught. The value is 3 into 10 to the power minus 8, right? So they're asking me find force per coulomb. So force per unit coulomb. So how do I find that? By putting the values 6 into 10 to the power minus 8 upon 3 into 10 to the power minus 8, which is 2 newtons, right? Sorry, 2. It is not newtons. Let me go. Yeah, 2 Newton per coulomb, right? So you can write it like this, Newton per coulomb. So this is for 1 coulomb. So for 1 coulomb, I have how much force? 2 Newton. Now, there is another part of this question. Using this result, predict the force that a charge of 12 into 10 to the power minus 8 will exert or experience. Sorry, not exert, it will experience. How much will this charge? How much is the charge for the B part? 12 into 10 to the power minus 8 coulombs. It's like saying I bought one chocolate, okay, for $10. And then how many chocolates, let's say how much I will be paying for 20 chocolates, right? So if you know the price for one chocolate, you can find for 20, okay? So one chocolate cost me $10. So 20 will be costing me 20 times 10. So this would be my answer, 200. So I know the force that is that is being experienced for by 1 coulomb. How many coulombs I'm looking for? 12 into 10 to the power minus 8. So what would I do to solve this question? I will simply do this thing which I did over here for the chocolates, right? So I will say, okay, um, a charge of 12 into 10 to the power minus 8 coulomb, which is this one, would experience a force of how much? 1 coulomb is experiencing 2 Newton. So I will multiply this number. So 12 into 10 to the power minus 8 coulombs will be experiencing 2 time 2 Newton per coulomb times 12 into 10 to the power minus 8, right? So let's say this is the cost of one chocolate and these many chocolates I am trying to buy. So how much I will be paying in total, something like that, right? I know the force for 1 coulomb. I have to find the force for this many coulombs, right? So you multiply. So the answer would be 2 times 12, 24 into 10 to the power minus 8 newtons. Okay, remember this is in coulombs, right? So let me write down over here. Let me make some space by erasing this example. Now, I have 2 Newton per coulomb times 12 into 10 to the power minus 8 coulomb, right? So I have something like this. So this coulomb and coulomb will be cancelled. So I will have 24 into 10 to the power minus 8 Newton as my final answer. Make sense? Okay. Now let's move ahead. So this is the in detail solution. Okay, you can pause here for a while, read through the explanation, and then you can move on. Next, this we already talked about the definition of electric field. Okay, that exists at a point is the electrostatic force experienced by a small test charge Q naught placed at that point divided by the charge itself. Okay, E is equal to F upon Q naught. Okay, I will not go into the details now. Units also we discussed Newton per coulomb. Okay, so it is the surrounding charges that create an electric field at a given point, right? So you saw in the example, you had a metal sphere over here, you had a metal sphere over here, and then you had an ebonite rod, and then there is a small point charge, right? So these all charged bodies, okay, surrounding charges, they are creating the electric field. Any positive or negative charge placed at the point interacts with the field. So if you place, let's say last time we placed plus 3 into 10 to the power minus 8 or 12 into 10 to the power minus 8. So if you place any charge over here, and that will experience um, a force, okay. Now let's see, here we have a question. The charges on the two metal spheres. Do you see the metal spheres in the figure over here? So we have two metal spheres, and then we have an ebonite rod. They create an electric field at the spot that is indicated. Okay, this field has a magnitude of 2 newtons per coulomb. Okay, so they're creating the electric field. The electric field value is given to 2 newtons per coulomb, and is directed as shown in the drawing. So it is like this, the direction is shown as well. Determine force on a charge that is placed at that spot if the charge has the value of q naught is equal to 18 into 10 to the power minus 8 coulombs. Okay, we'll talk about the b part after we are done solving the a part. So the electric field at a given spot, which is over here, okay, uh, can exert a variety of forces, okay, depending upon the magnitude and the sign of the charge placed there, right? So you know that, depending upon it's positive or negative, so it can, the electric field can vary. So this sign of the charge, what's its magnitude, right? The charge is assumed to be small enough that it does not alter the locations of surrounding charges that create the field. So we say that point charge because it's so minute, it doesn't interfere with the surrounding charges that are creating the field, right? These three things. Now, how do we find first part? Determine the force. We are looking for force. So let's see that. Okay, what we are given is electric field. So let's write electric field is over here 2 newtons per coulomb, right? And what else we are given? We are given this thing, the charge value q naught. So let me quickly write that 18 into 10 to the power minus 8 coulombs, right? So do you know a relationship that connects force, electric field, and q naught? I think I know. The formula is E is equal to F upon Q naught. But since this time I'm looking for force, okay, so I will isolate force and I will multiply E in times Q naught. I'm rearranging my equation. So electric field is 2, Q naught is 18 into 10 to the power minus 8, simply using these numbers to find the force. So force comes out to be 36 into 10 to the power minus 8 newtons. Okay, so this is 36. And this is the answer for the A part. Feel free to pause the video and try the B question, the B part. For the B part, again, you have to determine the force on a charge placed at the spot. If your Q naught value is 24 into 10 to the power minus 8 coulombs. So let's see. Again, let's write what is given to us. Electric field is given to us. Q naught value is given to us 24 into 10 to the power minus 8 coulombs, and F is something we are looking for. So last time we saw the formula comes out to be E times Q naught. So E is true and Q naught is 24 into 10 to the power minus 8, right? So we have 48 into 10 to the power minus 8 newtons as my answer. Forces in newtons. So if you look at the force on the negative charge points in the direction opposite to the force on the positive charge. Okay, so if you see over here in the diagram, so the this charge, this is negative. Okay, So here in the question, let me just write that this is mod. Okay, this is modulus. So this is minus. There is a minus sign, so I think the negative is missing over here for some reason. So this is, the more correct formula or the correct form. You must remember that you take the magnitude F upon Q naught magnitude. Okay. So electric field value were right in both cases, in this and this. But if you look at this situation over here, it was positive, and in this it is negative. So since Q is positive, the force points in the same direction. Because if you look at the formula, electric field is equal to force upon Q naught. Now Q naught was positive, right? Q naught was positive. So what does this mean? Electric field and force, they go hand in hand. That means they are in the same direction. Okay. So electric field, if you can see, and the force, they're in the same direction. Force is in this direction. Electric field is also in the same direction. And if you look over here, this is minus. Now for the B part, Q naught is negative. So what will happen? E is equal to F upon Q naught, but in this time, this is minus, right? For the magnitude purposes, it's fine. You can take it as positive, but now electric field and force, they are in the opposite direction, right? So force is in this direction and electric field is in this direction. So the negative charge points in the direction opposite to the force on the positive charge, that is opposite to the electric field. Okay, now let's move on to the next part. So this is a detailed solution. You can pause here, read the discussion, read the explanation. Okay, electric fields add as vectors too, right? Because we were just discussing that electric field is a vector quantity, and in our previous video we were just adding the x components, right? And we were adding the y components along the y-axis. So these are vectors, so they add. So electric field is also a vector at the end of the day, and it will add like other vectors. So here's a quick question so that we can get our hands around that. So it says that here's a figure that shows two charged objects A and B. Do you see them? Each contributes as follows to the net electric field at point P. EA is equal to 3 newtons per coulomb directed to the right, and EB is 2 newtons per coulomb directed downwards. Does it make sense? So EB, the magnitude is given and its direction is given it's downward. And for EA, its magnitude is given 2 and then it is directed. E is given 3 newtons per coulomb and it is directed towards the right side, right? So something like this. EA and EB are perpendicular. What is the net electric field at point P? So you see that because they're coming like this, and if I join this, so they are at right angle to each other, they're perpendicular. That is safe to say. Now, what is the electric field that is present at this point? How do we find that? So simple, like we did in our previous question. You can check my previous tutorial on force on a point charge due to the presence of two or more point charges. So there we solved this two-dimension question. So let's say you have f of x, you have f of y, and then you're looking for the resultant. So what you will do, how do you find the net force or the resultant force? So it goes like this, simple. So f of x squared plus f of y squared, right? So instead of f, what we have over here now, we have EB over here, and then over here we have EA. Everything else is same. This point is P. So this is your net electric field. Okay, so this is your net electric field. So this diagram I've drawn it over here. So whatever we will do, we will simply replace F with E, and that's simple. So E square plus EB square, right? So, okay, I know EA, it is 3. So let's put 3 over here. Do you know EB? Yes, it's given 2 square, very simple. So I have 3 square, which is 9, 2 square is 4. So 9 plus 4, that is square root of 13, right? And let me put that in the calculator, square root 13 real quick. It gives me the answer 3.61. So this is the magnitude of this resultant electric field or the net electric field over here, right? So 3.61, what are the units? Don't forget Newton per Coulomb. And do you remember how we can find the direction or the theta? It is tan inverse of EY upon EX. Students sometimes they get confused. EX is on the top or EY is on the top. So EY. So instead of EY, we have EB in this case, and we have EA. Okay, so let's do that. Let's plug in the numbers. EB is 2 and EA is 3. So let me just do 2 upon 3. 2 upon 3.666, and then the tan inverse of this number would be, the theta is coming out to be 33.7 degrees. Okay, so this is my answer. Okay, so this is the net electric field at the point P, which is 3.61, and then the direction will be along 33.7. Okay, degrees. Now moving forward, let me just erase that. You can try solving this question. You can pause, for a while. Feel free to solve it. So we are talking about point charges. A more complete understanding of the electric field concept can be gained by considering the field created by a point charge. So there is an isolated point charge Q plus 15 microcoulomb in a vacuum at the left. If you see over here in the figure. So in the figure on the left hand side. I mean, the figure is on the right hand side, but in the figure, if you see the left side, there's a point charge. Using a test charge of Q naught, which is 0.80 coulombs. Okay, so here's your test charge. Determine the electric field at the point P. So what will be the electric field? And the distance is 0.20. Okay. So what is the aim? What's the goal? Determine the electric field. So this is what we are looking for. Okay, I like to write what piece of information will I what I'm looking for, and then what piece of information is given. So this is what is missing. Okay, and then given is Q value 15 microcoulombs, right? I'm also given Q naught value, which is 0.80 microcoulombs, right? And also I'm given R. R is 0.20, right? Okay. I need to find E. I just learned this formula, E is equal to F upon Q naught. I do have Q naught. F is not given to me anywhere in this question, but I'm given this thing, this piece of information. Using this piece of information, can I find F? Do I know something? Do I know relationship between these quantities? Yes. I remember the Coulomb's law. Coulomb law is F is equal to K Q naught Q upon R square, right? Does that make sense? Yeah. K value I know 8.99 into 10 to the power 9. Q naught is given 0.8 into 10 to the power minus 6. Q is given 15 into 10 to the power minus 6. and R is given. Feel free to pause, do the calculation on your own, come back and check if your answer is right. So 2.7 newtons. Okay, so this is F. So we found F. I believe we must have done the calculation. Okay, I just showed you over here because it was right in front of me. And I was looking for F to find E. So let's go ahead and do that. Okay, so let me make some space over here since we just solved this one. And now solve for F. So how do we do that? Sorry, solve for E. F is 2.7. Q naught is, how much is Q naught? Where is Q naught? 0.8 into 10 to the power minus 6. Make sense? So what you can do is you can divide 2.7 by 0.8. Let me just quickly do that. So 2.7 divided by 0.8 is 3.375. Okay, and this 10 to the power minus 6 can go on the top and become plus 6. So this is what my electric field looks like. Okay, this is what my electric field look like. 3.4. So I can round my answer. 3.375 can be rounded to 3.4 into 10 to the power 6. And this is electric field, so the units will be Newton per Coulomb. Does that make sense? Okay, now let's see what we have next. So it's the same thing. This formula over here, they just simplified one thing. Okay, so let me do that for you. So electric field is F upon Q naught, right? What is F? We just learned from the Coulomb's law that it looks like this. Instead of using Q1, Q2, because here we are using actually a charge, a point charge Q, and a test charge Q naught, right? So I'm just using those upon R square upon Q naught. This is what we got so far, right? I plugged in simply the F value over here, right? And then divided by Q naught, right? Okay, so if I try to simplify that, it should look like K Q Q naught R square, okay, and Q naught. So let me just tell you quickly one thing about maths. Let's say you have two ratios, A upon B divided by C upon D. So how would you solve that? How would you simplify that? So you will keep your this thing as it is, like I did over here. Okay, KQ. And this thing will flip. So D will go on the top and C will stay here. Okay, so you can see now which quantity went where. Okay, you can see that. So you can see that you can write one over here so that it makes more sense. So one goes over here in the top. Okay, anything multiplied by one will be that thing only. In this case, it's KQQ naught. So what I've got over here is I can get rid of a few things which are same on the numerator and denominator, right? So what's my final answer? Now what's left? K Q upon R square. Okay, so you can also use this formula to find the electric field value. Okay, so you can feel free to use this formula. You can do it in the previous way that we in which we solved our question. Okay, here is a practice problem. Feel free to stop here for a while and do the answers. And these are electric field lines. We will do that in the next video. Thank you so much.